Okay, so I'm going to talk about combinatorial null or nullstellensatz. I'm going to just say combinal or CN for the rest of the talk. And this would be sort of like a mixture of polynomials and combinatorics, just doing very marginal stuff. So, okay, has everybody seen this particular thing? So if I have a univariate polynomial, is my handwriting visible at the end? Okay. And this univariate polynomial has degree, say, t. Then, and if this univariate polynomial is non-zero, then if I evaluate this polynomial at any t plus 1 points, it will be non-zero at least one of the points. So, you take t plus 1 points, you evaluate, so take a set S, such that size of set S is equal to 1. Then there exists an element A in S, such that f of A is not 0 if f is not 0. So what this says is that if I have a polynomial given to me and if I can evaluate at t plus 1 many points and I've been told that the degree is p and it's non-zero, the polynomial is non-zero, then there must be one point where it evaluates to not 0. And what combinatorial nullstellensatz does is it generalizes this property. So I'll just state what theorem I will be using throughout the lecture. And I won't prove it until the end because I want to focus more on the applications of that theorem. So, what does conval? Okay, so I'm going to use conval. So what it says is that if I have a multivariate polynomial, so if I have f, which is a multivariate polynomial, and my degree of f. So remember how you compute degree of multivariate polynomials? It's like the total, sum of degrees. So degree of f is say p, which is say equal to p1 plus 1 to pn. This is important. And then, and my other condition given to me is that there exists a the coefficient of the monomial x1 to the power t1 over the xn to the power tn is non-zero. Then if I give you a set S, which is cross product of these SI set, and the condition I have is that SI is strictly, the cardinality of SI is more than TI. What it says is that there exists an element S1 Sn, which belongs in S1 cross Sn, such that this polynomial f evaluates at S1 comma Sn and is non-zero. It looks a bit complicated, but when you just restrict this to n equal to 1 case, it's basically this. When n equals to 1, my Si just becomes S1. My S1 is basically a set of cardinality at least t plus 1. And I since my degree of the polynomial is p, then the monomial x1, which is now x to the power t, will have a non-zero coefficient. and precisely this will hold. So yeah, the statement is fine to all of you for Combinatorial test. Okay, so now we can start doing some problems. And the problems will be very combinatorial in essence. So yeah, I'll write down the problem. So it's been a while, but since I've done this is a Russia MO problem. I think it's a Russia 2013 Math Olympiad problem, which is very fun. Think about it. So I have given you 100 gone. So
It is 2007 P5.
which one?
Russia 2007.
Oh my god, have you done this problem?
Yes.
Okay, then if you're not able to solve this, we'll ask him for a solution. Yes.
It is a long time.
It's okay.
Okay, sure.
So I have given you 100 gone, and what you're doing is that it has 100 vertices. It's a polygon with 100 vertices, and on each vertex, I'm writing two distinct numbers on each vertex. So let me write this down. Each vertex, you're given two distinct numbers. Integers. Then show that there is show that there is a way of numbering the vertices such that the label is basically from one of the two neighbors in the labeling I have done, and make sure that the adjacent, so I'll just write this down. I should write it out form. Means that, okay, show that one can remove a number from each vertex so that the remaining numbers on any two adjacent vertices differ. Is the problem statement clear? So I'm giving you 100 gone, and each vertex I have written two numbers, and those two numbers are distinct. Then I'm asking you to remove one number from each of the vertices, so that now in my 100 gone, if I have two vertices which are adjacent to each other, that is there is an edge between them, then the numbers written on those two vertices differ. So if you are from a CS background, then there is something called greedy algorithm. So so one approach to this is doing greedily. Might not work. I mean, it doesn't work. So what happens when we think about greedy stuff is that you pick a vertex and you're like, I go to the next vertex, it is adjacent to, if they have anything in common, I just remove that number and iterate this process. And the thing is, this process doesn't work. So another thing is the 100 thing necessary? Like, if it is not necessary, what is the necessary condition? So probably even. Do you think it's true for all?
No, it can't be true for all. Just take 1 to 1 to 1.
Yeah. So it's not true for all. So a hunch is maybe it's true for even. Spoiler alert, yes, it is true for any even. And so obviously we're going to use combinal for this. But if you have any non-combinal approach, let me know. Let's think about it. And the communal approach would also sort of encapture why we are why even is necessary. Okay. So I took an example for this. Let's just say I have square and I write 0, 1, 1, 2, 0, I guess, maybe 1, 2. So a valid coloring, a valid picking would be maybe this. This is fine. So the adjacent things differ from each other. And yeah. So the way you approach these combinatorial objects is that you want to find a polynomial. And remember what is happening in this thing. We are given, so we have to then find out sets S1 to S1 cross Sn, such that we can choose some element from these cross product of sets. So here also there's some choosing going on. Like we are choosing. So it might be a nice. So this is like approaching from backwards. But if combinal might be used, then you have to. Then this possible sets would be these vertices, the set of numbers labeled on each vertex. There will be 100 sets, so maybe 100 variables will be there for you. But then you also need this condition that the SIs, the cardinality of each SI must be strictly greater than TIs. So what polynomial you want. And you want your polynomial to also encapture that the adjacent vertices are not same. How do you do that? So I don't want to spoil, but I have to spoil. So you have done it. Okay, fine. This power statement is simple. I just want you to give me a nice polynomial that the sets are ready. Sets are these things. So which polynomial do you think might work? So, okay, how about you say the polynomial? Say the polynomial.
Take the difference of each of the vertices and yeah.
I see. Okay, maybe we'll see what he's saying. So if I'm not wrong, he's saying that. So
the labels are like x1, x2, then we take x1 minus x2 minus x1, x3 minus x2.
Okay. So we want obviously our polynomial to be a variable, to be having variables x1 to x100 because it's a 100 one, and we want the polynomial to encapture that the adjacent vertices labelings are distinct. So how do you encapture that? That is encaptured by the polynomial x1 minus x2, x2 minus x3. So xi's are the labelings on the vertices. x99 minus x100. x100 minus x1. Okay, I have a polynomial. I'm not sure if that's the polynomial which will work. But, okay, let's just see. What is the degree of this polynomial? 100. So, degree of P is 100. Okay, cool. My sets would be the set of vertices labels I've given. Sure. I also, so, I want a monomial, right? I want at least one monomial which satisfies this properties. And so, yeah. Which monomial should I choose? Is the question. Is my question clear? So here we want that for this combinal to work, I want a monomials with the following degree such that the coefficient of this monomial is non-zero. My question to you is that 1, what is that monomial? 2, what is the coefficient of that monomial? Remember, I have my SIs to be 2 because I have 2 in each vertex. So it would be nice that my TIs are 1. I mean, TIs being 0 is just nonsense. So if TIs are 1, that would imply that my monomial I'm looking for is just x1 into x2. Okay, sure. Let's go with the monomial x1. So we go with the monomial x1, x2, x100. What about what's the coefficient of this monomial in this polynomial? Is so I hear 2. Do you guys see why it's 2?
Yes.
It would be 2. And the coefficient, so it's just like one comes from this, the other comes from the last. So now do you guys see why 100 being even is enough?
Otherwise, the other one will be negative and then.
Yes. So coefficient is 2. 2 is not equal to 0 in this in non-zero. Sorry, yeah, in rational sense. So the coefficient is not equal to 0. Then I can just spam this. I can spam combinal. What does my combinal say? My combinal says that if I have this thing being satisfied, then I can choose S1 up to S1 up to S100 such that this polynomial in this S1 up to S100 is non-zero. Do you see that? I mean, that's what combinal says. So, guys, there exists S1 to the S100 from my sets here, such that TS1 to the S100 is non-zero. And if it's non-zero, then we're done because that implies that these S1, S2, S2, S3, S3, S4, and S100, S1, they all differ. And that is all we wanted. So this thing over here, I mean, I just get an existence too. I don't get a construction. So, yeah, but we're done with the problem. Very fun problem.
Is there an algorithm?
I actually tried to think of it. I couldn't come up. I mean, but the only thing I thought of was greedy. I couldn't come up. But maybe there's something else which might work.
I was first we will assume that we can make this problem as harder. So we can assume that every number is shared with at least one consecutive numbers. Because otherwise you would just change it and it would be a strictly harder problem.
Yeah, no, actually I thought of that too.
Yeah, I was thinking first we can do that and then we can label the edges by the numbers which are at both sides.
Right.
And then if we can label the edges, when we have one very nice thing that if two edges are labeled the same thing and they are separated by more like this, then there has to be the edge between them also has to be labeled. Right, so if they are not connected to each other, then they are separated by at least 2.
Right.
Because otherwise the center one would also have to be labeled. So basically then we get in the lines, I don't know what the word, but like consecutive edges which are labeled by one number, consecutive edges which are labeled by another number.
Yes, yes.
And then I guess we can alternate other numbers in that consecutive labeling.
My whole thing is that reduction actually correct? Because when I do not have like vertices which do not share, like I have more degree of freedom. But then I also have to, but then, like, sorry, I can't formulate it properly, but it might end up actually
It's hard to
getting,
predict what happens at the
yeah,
end.
it's hard to predict what's happening in the end. And it's not a strictly harder problem if,
I mean, let us say that we have some form from something which works for a harder problem, what I am calling harder problem, right? Then you can just change it back to the previous problem.
the thing is,
Then the same solution will also work because if the numbers are different now, they are still different. We are not enforcing any
yeah,
inequalities.
yeah. The thing is, the same solution might not work. And I'll talk to you after this because I actually thought about this.
Okay.
So, and I'll tell you what happens. Okay, so this thing is nice. Next is a very nice, another nice combinatorial object you'll see is, so the theorem is called Cauchy-Davenport. Very fancy name. It's by Cauchy and Davenport. So say I have two subsets A and B, and they are subsets of Z not PZ. So they are subsets of FP. So they are numbers of the form 1 not P, 2 not P. Like they're subsets of. So everybody is fine with FP, right? So I'll use it. Then I consider the subset sum of A and B. Do you guys know? I mean, I'm just so, yeah. I just look at A plus B, which is basically taking elements from A and taking elements from B and adding them. And you're doing it modulo B. So, yeah. Cauchy-Davenport gives you a nice lower bound on this set A plus B. It says that the cardinality of set A plus B is minimum of P or mod A plus mod B minus 1. Again, I have given you this problem. It looks very combinatorial, but the solution it's going to use is very polynomial. So, yeah, it's nice to know algebra.
Do you hint to us the integration for this?
I give you, so I mean you came a bit late,
I'm
but
sorry.
I define, I mean the tool we are going to use is this something called Combinatorial.
I know, I just need an integration because this is seen that in the
So I think actually you should think about contrapositive way. What happens if mod A, like the cardinality of A plus cardinality of B minus 1 is strictly greater than A plus B, the cardinality of A plus B? That would help. So, I mean, there's one easy case which we can think of. So everybody is fine with what A plus B is, right? Okay. And everybody is more or less convinced that what this theorem is saying. So now let's try to prove it. And there's one easy case. One easy case is when A plus B, sorry. So I'll just write it. This one. When A plus B minus 1 is greater than B.
Yeah,
No,
this is,
Huh?
yeah, this can be solved by,
Oh, yeah, go ahead.
so mod A plus mod B is greater than equal to P plus 1. So by PHP,
Yeah,
so there will be two numbers which is in A and B2.
yeah.
And now, like basically, because two numbers are same, what else is going to say?
You would like to show that A plus B basically captures every number in FP. So you'll have to show that every number in FP can be written as a sum of element from A and element from B. So, yeah. But he's pretty much right. So, note that the set A plus B, the cardinality of this set will be at most B because we're dealing with FP.
Yeah.
So, I want to show that when mod A plus mod B minus 1 is greater than equal to B, then this set A plus B is P. So, the cases are two cases, like if this is greater than equal to P or it's strictly less than P. So, let me just write the two cases. At both the cases, I want to show that A plus B is strictly greater than is greater than equal to mod A plus mod B minus 1. So, or it at least achieves this. So, the proof of this first case is done, basically what he said. So, if I have mod A plus mod B minus 1 to be greater than equal to P, then I want to show that this minimum P, this thing is P. Then you want to show that mod A plus mod B is equal to P, at least, but it's going to be equal to. And that you have to show that every element in, so you want to show that for all element in FP, there exists A, B such that U is equal to A plus B. You just want to show that. If you show that, then this case is done. And for every U. So now, it can be, this can be done by PHP. So the way I thought was that, suppose you cannot express U as sum of A and B. Then, if the elements of A are say A1 up to AL, then so suppose not, and elements of A are say A1 up to AL, then B cannot contain U minus A1, U minus A2, U minus AL. This already gives an upper bound on the cardinality of E. If I'm just going in the contrary way, then so these things do not belong to B. So do you get an upper bound on? Do you guys see an upper bound on? Oh, sorry.
N minus L, less than equal to N minus L, the cardinality.
Yes. So the cardinality of B is less than equal to P minus L. But you're given that the cardinality of A plus B is strictly greater than B plus 1. Greater than equal to P. And this gives you a contradiction. So, this intuitively makes sense. You just have way too many elements given to you. So when you add them up, you'll end up covering the whole set. So this proof just essentially encapsulates that. Okay, fine. The polynomial span will be used here. If I have mod A plus mod B minus 1 to be strictly less than P, then I want to show that mod A plus B is strictly is greater than mod B. Mod B minus 1. If I show that, I'm done. Because the minimum of this when this object is less than P is basically this. So I just want to show this. And as I said to him, we'll just go in the contradictory method. We'll use method of contradiction. And how would we do it? So I want some nice polynomial to encapsulate this thing. Yeah. So suppose now. Suppose you have A plus B to be less than, strictly less than mod A plus mod b minus 1. You would like to get some contradiction, and I want you to use polynomials. So what I'm going to do next is a bit black magic. Not black magic, but it's a bit, yeah.
Like x power ai's, the sum of x power ax multiplied by the sum of x power ai's.
Oh, okay. So your polynomial is saying this. So the thing is, I also want a bound on my. Degree. So, and how many variables do you want to introduce?
I just had one variable.
I see. So I'm not sure if that would work because the set which is given to us is sort of like two set. So you would likely like to have two variables. So I was thinking, so at least the method I know uses two variables. Maybe we can think about it. Okay, so any guesses on what the polynomial would be? So,
Is it trivial enough?
huh?
Is the polynomial trivial enough?
No.
Okay.
Like sort of like this. It's my talk right now. The poker night happens at 10 something. You guys informed us.
Okay, for the second reason, I think is Bentley Automata, the algorithm that you're looking for. Not exactly Bentley Automata, but you could do some modifications with Bentley Automata to solve this question.
I don't know much about how it was in that. So you can tell me later.
Right.
So anyways, let's focus on this and let's quickly get a polynomial for this. My goal is to solve a P6 animal and then show you.
But it was 7
On
ideas.
when we were talking about it, like I mean, I was told it's 1 hour and it started 9:50. So. Okay, let's quickly do this. So the polynomial we're going to work with is going to be a degree, it's going to use variables, two variables, each for sort of like the A and B's.
Can we
Huh?
take the polynomial where it's a product of product A plus B minus minus the elements that are in A plus B set.
That was the one which I was going for. So you want to sort of x plus y minus s where s belongs to a plus b. So note that this polynomial becomes 0 at precisely the elements of a plus b. And I know the degree of this polynomial. The degree of this polynomial is just the cardinality of a plus b. So the degree of p is cardinality of a plus b, which is less than mod a plus mod b minus b. How will I use it? God knows, and we'll figure it out. Okay, cool. Now what? If it is the polynomial, which I have already spoiled that it is the polynomial, I still want to prove the statement, right? So how do I want the monomial to work with is the question. I want a monomial to work with, and I want my sets to be A and B. So my monomial's degrees should be like at most mod A minus the cardinality of A minus 1 and at most the cardinality of B minus 1. So that sort of tells you and the degree of the total degree of the monomial should be the degree of this polynomial mod A plus B. So I'll just give you what the monomial is. The monomial is going to be, any guesses? Any guesses on the monomial? Okay, everybody's thinking. I will see.
How absolute value of how absolute value of A is by forward.
So I want my monomial degree to be strictly less than the sets I'm choosing from, the cardinality of the set. So it's not
It's to the power A minus 1 into y to the power cardinality.
and I want the total degree to be mod A plus B.
Yeah,
So I'll just make
B minus, yeah, A plus B minus 1.
it should be this. Rather. Like I want the total degree to be mod A plus B. Okay, fine, sure. What's the coefficient of this object in my polynomial? Simple combinatorics should be able to do it. Okay, nobody can do it. No. The coefficient is
A plus B, choose A minus.
yeah. Choose A minus 1. Basically, like I have to just choose where my x's are being taken from. Okay, so
You choose A minus 1 or choose A minus B?
A minus 1.
the degree of x is mod A minus 1. No worries, it's okay. Okay, sure. Everything is fine. If I want things to work out, I at least first want that coefficient to be non-zero.
It is
Why is it non-zero?
mod of A plus B is like strictly greater than
Strictly less than b.
mod of A plus B is like greater than equal to mod of A. So
Yeah, okay, fine. But it's still so. Sure. My whole problem is that the field we are working with is FP. So that thing can just become 0 mod P.
oh yeah, that's true.
But can it become 0
You
mod
can
P?
just take one constant element of B, add it to the element of A. If A is and B, this is trivial.
Oh, sure. I mean, there's a much simpler
We
way.
can just
That mod A plus B is so mod A plus B is strictly less than P. Because we have assumed that mod A plus mod B minus
we
1
can't
is.
divide.
Yeah, so P can't divide that object.
Yeah.
Because it's like an object strictly like, yeah, so it's non-zero. And here we are using the fact that we are working in FP. So, okay, this is non-zero, cool that. But now what? What would I get? I'll get that there exists an element, so everything is satisfying the combinal property. So I'll get an element A comma B. So there exists an element. So, okay. Can I use combinal? So I have my sets to be my S1 to be A and my S2 to be B. A is surely greater than mod A minus 1. But I want my B to be greater than mod A plus B minus mod A minus 1. But that is ensured by this thing. B is, because I have assumed that mod A plus B is strictly less than mod A plus B minus 1. This mod A plus B minus A minus 1 is strictly greater than 1. So I can use combinal. But what does combinal give? It gives me that there exist points A comma B which lies in A cross B such that P of A comma B is not equal to 0. You will see a contradiction. This is a contradiction because I have constructed my polynomial in a way that it will be 0 at points which are in which are in A plus B. So I get a contradiction. And the contradiction is coming up because I have assumed that, because I am assuming that the cardinality of B is strictly greater than the cardinality of A plus B minus A minus plus 1. So this is such a combinatorial statement. I'm just like adding two sets and then I'm just using polynomial spamming everywhere to do this. So pretty fun. So yeah, this is one. I also want. So I have like 20-ish minutes left. I'll end at 10:15. So I want to quickly just do I or 2076. which is known to be notoriously hard. Well, it's not that hard if you know what combo null is. This is my advertisement for combo null. I think.
If you don't put it in a common, it's hard to think that it's common.
Yes, that is true.
Everything is simpler in hindsight.
If you know enough things. If you know enough things. So, okay, so
Component makes the problem easy.
yes, like
But in this case, I think significantly easier than that.
I mean, not easy. Okay, so like the thing is, the important thing about combo null is you should know how to find the right polynomials. So in a way, it's like, I mean, since I used to do geometry when I was young, so the way I used to approach geometry problems were like sort of like finding clues. And here you have the hunch that which sets you want to work with. And I just now want a nice enough polynomial. So yeah. And I'm a 2007 P6. So some background, there were 500 plus participants in that IMO and only 5 were, you can wait till, I'm just doing IMO 2007 P6. Have you done it? So I'll write the problem statement and then I'll probably erase that word over there. So 500 participants were there, only 5 were able to solve this. So it's a pretty hard problem. So let n be a positive integer. And you define this following set. It's a 3 tuple, it's a set of 3 tuples. And the 3 tuples are nice. These, they belong in this. So all these x, y, z speak values from 0 to up to n. But I just don't want them to be 0, 0, 0. So what is the cardinality of set S? Cardinality of set is basically, I want to
I think it's 2 months to think about these problems.
Oh, okay, sure. The cardinality of S, I haven't written the problem down here. So the cardinality of S is basically n plus 1 cube minus 1. Pretty simple. Then your job is to determine the number of the smallest number of planes such that the union of these planes contain S, but it does not contain 0, 0, 0. So it's a problem statement here. It says that I have my positive integer n, and I just look at the set of all 3 tuples, and these 3 tuples are of the forms, we take values from 0 to up to n, but this set does not contain 0, 0, 0. So this set obviously is of the size n plus 1 cube minus 1. Your job is to determine the number of planes. So planes are basically and these planes cover basically contains S, so they cover S, but it must not pass through 0, 0, 0. So they don't pass through the origin. So as most of you guys want to try this problem, try it. I will. Yeah, just try it.
I have most of them like they couldn't prove the construction, but most of them guessed the answer.
The answer is easy.
Yeah, obviously, but how would they get any points for guessing? Would they get 1 point?
It's a P6. P6 usually
They give 1.
they do give 1. I think I'm not sure about what the thing, like what the party was, but usually if you guess it, you have some. contestant guessed 3n, which is the guess. Then they won.
Like I've had most of the.
In 3 is easy to
I don't think marks are given for guessing the answers and I won't at any point in time.
You know it is.
I mean, if you
It's not an IMO.
No, if you saw construction, like last year P6, they gave awards for construction.
Last year P6 was rage bait.
Okay,
I mean, it was really guessing by
Guessing.
the answer was such.
So let's not dive. I just want you guys to solve this problem.
I have seen the solution before, but I like remember parts of solution.
Yeah. Pehle, huh. Okay, give me the 3 ends. Like, I told it's 3n, but can you guys tell me which planes will work?
Diagonal.
Cut it down.
The
Yeah.
diagonal is perpendicular to the mean diagonal.
So,
Or parallel.
Basically, x plus y plus z equals
Yes.
yeah.
I for I equals 1.
Yes, precisely. Maybe I'll.
You can multiply the planes.
I can multiply the planes.
Yeah, for the
That's
whole.
what J equals. So, construction 3n works, and the plane we get is just x plus y plus z equals to I for I being in 1 to up to 3n. So note that these planes do not capture 0, 0, 0 because precisely we're taking I from 1 to 3n. Okay, 3n planes. Now I want to show that 3n, say come, it does not work. And I mean by now you might have seen how we are using combo narrative. We're sort of like obviously we'll go with the method of contradiction. But we want sort of a polynomial which can capture all the points and only the plane points. So that's I mean I'm just giving you dropping some hints and get some contradiction. So yeah. Okay, I will wait for like a minute at most because I have to wrap up. Because there are people over there waiting for poker.
I think like there were 2 sets for sure. Like we kind of define 2 sets and what from that I think.
2 sets. We define 2 polynomials and work.
Yeah, 2 polynomials. I mean not 2 sets, 2 polynomials.
Yeah, so we define 2 polynomials. One with encapture. So yeah, think about it. So I mean, these polynomials are doing nothing but encapturing the object we want to encapture. Like here it's encapturing the thing, like then it's encapturing the condition that note, oh he's here for poker now. Never mind, so here it's encapturing the fact that no two adjacent vertices labeling are same. Here it encaptures that there is an element which is sum of two elements in A and B. I want here, what are my 2 conditions? My condition 1 is that it needs to be part of a plane. And condition 2 is that I don't want x plus y plus z equals to 0. Or I don't want x equals to 0, y equals to 0, z equals to 0. So, what do you do for this?
One polynomial would be x minus I, x, y minus I.
Sure, yeah. Okay. So, one polynomial is. But where am I running it from? Like from what to what?
One.
From? I equals to
1 to
1
n,
to
right?
Huh?
We can run it from 1 to n possible.
Well, z can be. Huh?
0 to n minus 0.
I don't want it to take zeros, so fine. I mean, people can work with put x plus y plus z minus I also. That is fine. What do I want from my other polynomial?
Is it a plane equation?
Yes.
Capturing the plane equations?
Yes.
I was thinking about.
So I essentially we want to work with method of contradiction. So let's say we have k planes, and the k planes are strictly less than the k is strictly less than 3n. So then my plane equation, the corresponding plane equations, it's going to be some like ax plus bx plus cy minus d, but then corresponding to each of the planes. So for each plane, I have some apx, bpy, cpz plus d. And it's going over things. So now I think we can start seeing, like obviously those two are the polynomials we are going to deal with. What is the degree of the polynomial qxyz? 3n? Okay. Let me remove this thing. What is the degree of the polynomial pxyz?
Number of planes?
Number of planes. Okay. Degree of p is k, which is the number of planes. Which is strictly less than 3n by our assumption. And degree of q is 3n. Again, we are backtracking. What do you think our sets would be this time? I want again my set to be strictly more than the degrees. So, and the degrees, if I am sort of, hopefully, I want my degree for each variable to be at most n. So my sets can actually be precisely 0 to n. 0 to n.
You are not allowed to pass
Yeah,
it, right?
right.
You are not allowed to pass it, right?
Am I allowed?
You're not allowed to pass it, right? Coordinator planes. Your planes are not allowed to pass it.
Yeah, they're not allowed.
Right,
So we'll get a contradiction if we get some.
Can we just take two difference? We can see the formula for the second one will be non-zero and 0. We can just take difference, the top would even
That is precisely what we are actually going to do. We're going to take some difference, but then I want. Okay, so his idea is basically.
we did difference when the zero.
Yeah, but you have to also take